So let's work out what this capacitance would be for a parallel plate capacitor. Now you remember we talked about the fact that if I have two charged plates, the electric field between these plates is going to point from one to the other. So that's the direction of the electric field between the plates, because electric fields due to the positively charged plate point away from the plate in both directions. Electric fields due to the negatively charged plate point towards the plate in both directions. And if you remember, we said that the electric field due to a plate, doesn't change as you move away from it. So the electric field that's pointing towards the negative plate and away from the positive plate on this side has the same magnitude, so they exactly cancel. The electric field pointing towards the plane and due to the negative plate and away from the plane due to the positive plate on this side again cancel because they have the same magnitude. However, in between them, the electric field due to this plane points away from it. The electric field due to this plane points towards it, so they add up. Okay, and that's the value of the electric field in between the plates, so, and it's 0 outside. Approximately. This is true for infinitely large plates, but as long as the separation between the plates is much smaller than the size of the plates, this works well. So this is a bit of an idealization. It's usually these dimensions are quite different. Okay, so how would I calculate the voltage difference between the plates now? Remember, voltage is, so the change, the work done by the electric field is equal to negative delta U. So imagine I'm moving from the positive plate to the negative plate. Let's say I'm moving a charge Q from the positive plate to the negative plate. I have this electric field E. So the work done by E is going to be equal to the change in potential energy. Now what is the work done as I move from the left plate to the right plate? The work done is going to be let's try this again. Force times displacement times the cosine of the angle between them. So imagine I put in a little charge Q and I want to move that from the left plate to the right plate. What is the force on charge Q? There's an electric field with E between the plates. In terms of the electric field E, what is the force on charge Q? QE, right? Q times E is the force on charge Q. That force is not changing as I'm moving from one plate to the other, because you see this expression, it depends on the area of the plates. So in this expression, Q is the charge on the plates, A is the area of the plates, cross-sectional area, and epsilon naught is a constant called the permittivity of free space. So when I move from left to right, I've only written part of that equation down. The force is Q times E. What is the displacement if the separation between the plates is little d? The displacement is just d. What's the angle cosine, the cosine of the angle between those two, the force and the displacement? The angle is 0, so the cosine of the angle is 1. So that's just it. That's the work done. So as I move charge Q from left to right, I get Q E D is equal to U initial minus U final. But U is just Q times V initial minus V final. By definition, I have U is equal to Q times V. U, the potential energy, is the potential times the charge. Or if you like, electric potential is potential energy per unit charge. So this, comparing these now, if I divide this both of these by Q, what I get is the potential difference between the two plates is just E times D. Now you remember we said the capacitance by definition C is Q over delta V. Okay, so what I've written over here, let's say Q over change in potential. Let me write V initial minus V final. It's not delta V, it's negative. You know, it's the positive value of that. So what I'm going to get is C is Q over E times D from this. But now I know that E over here, I know that E is equal to Q over A epsilon naught. So let me replace that in here. Q over E, which is Q over A epsilon naught times D. So the Q's are going to cancel, and I can bring A epsilon naught to the numerator. So I have epsilon naught A over D. So this is the capacitance of a parallel plate capacitor. And remember, I said capacitance is a purely geometric quantity. If you see this formula, you see it depends on this constant, which is a universal constant, epsilon naught. It depends on the area of the plates. So if these are square plates, the area is just the square of the side. If these are circular plates, the area will be pi r squared, which is like one of the problems you had on mass physics. And little d is a separation. So this means if I have more area, I can store more charge. So capacitance, remember, is your ability to store charge. The larger the capacitance, the more charge I can store. Okay, and you can see this by looking at this definition of capacitance. So this tells me the charge I can store depends on the capacitance and the voltage. So I can store more charge if I have a larger capacitance. How can I have a larger capacitance? I can have more area, or I can make the separation smaller. I can also store more charge if I increase the voltage. So that's the definition of capacitance. And this is just going through that.